On November 9th, astronomers encountered something in space that, by all established understanding, should not exist. What appeared in the data was not subtle or ambiguous, but stark and confrontational. A set of razor-straight jets of dust and gas erupting from the interstellar object known as 3I/Atlas. These jets extended for more than 1 million kilometers, maintaining perfect alignment as if frozen in space, utterly untouched by the object's known 16-hour rotation. According to everything comet physics predicts, such structures should bend, smear, blur, or twist into spirals as the nucleus spins beneath them. Instead, they remained crisp, linear, and geometrically precise. This was not a marginal deviation or a small inconsistency that could be explained away with noise or uncertainty. It was a direct contradiction. What followed was not merely a debate about unusual comet behavior, but a deeper confrontation with the limits of current models for interstellar visitors and the uncomfortable realization that something fundamental might be missing from our understanding. The November 9th image captures 3I/Atlas suspended against a deep black backdrop, isolated and unmistakable. From the unresolved bright core at the center, a cluster of narrow white lines radiates outward in multiple directions. Some fan upward, others branch sideways, each one sharply defined from origin to terminus. Their edges are clean, their paths uninterrupted, even as they stretch far beyond the glow of the coma. The orientation of the scene is anchored by the sun's position, located off-frame toward the lower left. In that direction lies a broad, faint streak pointing almost directly back toward the sun itself. This feature, known as an anti-tail, forms when sunlight reflects off dust particles that lie between Earth and the object, creating the illusion of a tail that points sunward rather than away. While unusual, the anti-tail is at least a known phenomenon. What truly dominates the frame, however, are the other jets, multiple perfectly straight structures shooting outward at varying angles, none of them showing the arcs, curls, or diffusion expected from a rotating body. They appear locked in place, indifferent to the passage of time and motion. This image is not an artist's rendering, a simulation, or an interpretive composite. It is a direct astronomical observation captured by a major observatory and processed through standard reduction pipelines used across the field. The anti-tail may be labeled for clarity, but the true focus lies in the geometry of the jets themselves. Their straightness is not subtle. Their length is not modest. Their alignment is not coincidental. Together, they dominate the scene and force a single question to the forefront. How can such features remain so fixed and so precise on an object that is known, with high confidence, to be spinning through space? Months before the November observation, astronomers had already established a critical parameter that would later sharpen the mystery. During coordinated photometric campaigns in July and August of 2025, multiple teams tracked 3I/Atlas and measured subtle, rhythmic changes in its brightness. These variations, known as a light curve, arise as an irregularly shaped object rotates and reflects sunlight differently over time. By analyzing this repeating pattern, astronomers calculated a rotation period of 16 hours. This is not an estimate pulled from sparse data or a single instrument. The result was confirmed independently by several observatories, each ruling out contamination from background stars, instrumental drift, or transient artifacts. The uncertainty on the measurement was small, just a few hundredths of an hour. In the language of observational astronomy, this number is solid. A rotation period of 16 hours places 3I/Atlas well within the typical range for cometary nuclei. It is neither unusually slow nor catastrophically fast. Most comets in our solar system spin at comparable rates. But this number carries enormous implications. If the nucleus rotates once every 16 hours, then any jet tied to a fixed location on its surface must rotate with it. Over time, that rotation should imprint itself on the escaping material. Jets should sweep across space, tracing arcs or spirals as the nucleus turns. The longer the material takes to travel outward, the more pronounced this effect should become. This is not speculation. It is a direct consequence of geometry and motion. The significance of this becomes clear when considering the speeds involved. Dust particles escaping from 3I/Atlas are estimated to travel at around 400 meters per second, a value entirely typical for cometary jets. At that speed, reaching a distance of 1 million kilometers is not a quick process. 1 million kilometers is 1 billion meters. Dividing that distance by 400 meters per second yields a travel time of approximately 2.5 million seconds, or just over 29 days. During those 29 days, the nucleus of 3I/Atlas completes roughly 43 full rotations. That means a surface vent would point in every possible direction dozens of times, while its emitted material slowly drifts outward. The expected result is unmistakable: spirals, corkscrews, or at the very least, significant smearing and curvature. This behavior has been reproduced in laboratory experiments, observed in countless comets, and confirmed in numerical simulations. A rotating source cannot produce a long, straight, unwavering jet under these conditions. Yet that is exactly what the November images show. The jets remain straight for distances exceeding 1 million kilometers, as if the nucleus were not rotating at all. This is not a small discrepancy that can be explained by tweaking parameters. The numbers do not permit it. The physics demands smearing. The images show none. This quantitative mismatch lies at the heart of what astronomers began referring to as the 12th anomaly of 3I/Atlas. When the Parnell Observatory team began processing post-perihelion data late on November 9th, the reaction was immediate. Experienced observers paused mid-analysis, suspecting artifacts or errors. Raw files were rechecked. Calibration steps were reviewed line by line. Alternative reductions were run. The result did not change. The jets were real. Their geometry persisted across multiple frames and observation nights. The timing made the contradiction sharper still. Only months earlier, the rotation period had been measured with confidence. There was no evidence of sudden spin down, no sign that the nucleus had slowed to a crawl. Light curves remained consistent. And yet the jets refused to behave as they should. As word spread through internal reports and informal channels, disbelief gave way to urgency. Some researchers proposed exotic confinement mechanisms. Others revisited assumptions that had gone unchallenged for decades. A few raised uncomfortable questions about whether the jets were truly tied to the surface at all. The anomaly label stuck, not as sensationalism, but as a placeholder for a problem no existing model could solve. Several explanations were considered and weighed against the data. The reaction was immediate. Experienced observers paused mid-analysis, suspecting artifacts or errors. Raw files were rechecked. Calibration steps were reviewed line by line. Alternative reductions were run. The result did not change. The jets were real. Their geometry persisted across multiple frames and observation nights. The timing made the contradiction sharper still. Only months earlier, the rotation period had been measured with confidence. There was no evidence of sudden spin down, no sign that the nucleus had slowed to a crawl. Light curves remained consistent. And yet the jets refused to behave as they should. As word spread through internal reports and informal channels, disbelief gave way to urgency. Some researchers proposed exotic confinement mechanisms. Others revisited assumptions that had gone unchallenged for decades. A few raised uncomfortable questions about whether the jets were truly tied to the surface at all. The anomaly label stuck, not as sensationalism, but as a placeholder for a problem no existing model could solve. Several explanations were considered and weighed against the data.